Okay, hi everyone. We have finally come to the last chapter that will be included in the final exam, chapter 12, the first law of thermodynamics. For the most part of this chapter, we will be using what we have already learned about ideal gas in chapter 11. This chapter is actually quite a short chapter. There are only four learning outcomes. The first one is what a good number of you who have taken pure science in O level have already learned before, specific heat capacity and latent heat capacity kind of thing. Okay, it is actually quite simple, so there's no need to worry even if you are a combined science student in the past. The difficulty is nothing comparable to everything that you have already learned about in A level. And then for learning objective B is basically a small extension and a rehash of what we have already learned in chapter 11, where I have already introduced the term internal energy. I have also explained to you for ideal gases, internal energy is basically just the kinetic energy due to random motion. And then for intermolecular potential energy, it is zero because based on what we have already learned from the very first assumption in kinetic theory, intermolecular forces is basically negligible except during a collision. So that is why potential energy is actually zero. And then for objective C and D, they are basically the main new things. Okay. So without further ado, let's start. So for specific heat capacity of solid and liquids, to understand what exactly is heat capacity or specific heat capacity, let's think about this. Okay, if I actually heat up 1 kg of water versus 1 kg of oil, which one will actually gain temperature faster? Of course, it will be the oil. And why is that the case? In really technical terms, it is really because oil has lower heat capacity or specific heat capacity for that matter than water. We will differentiate between heat capacity and specific heat capacity in greater clarity later. Okay, but for now, the definition of heat capacity of a mass is basically the amount of heat energy needed to raise the temperature by unit temperature without going through a change in state. Heat capacity is basically notated by capital C, and the equation is basically just Q over delta T, which is basically the heat energy, the amount of heat energy divided by temperature. The SI unit is basically joules per Kelvin. And then for specific heat capacity is basically defined as the amount of heat energy needed to produce unit temperature change for unit mass of a substance without causing a change in state. Specific heat capacity is denoted by the small c, whereas heat capacity is denoted by the capital C. And the equation differs from heat capacity basically by the per unit mass. Okay, so essentially specific heat capacity is basically Q divided by M per unit change in temperature, or in other words, is basically the heat capacity per unit mass. To give you some context on why there is a need for two terms that are actually so similar, the idea here is like if you go to some old traditional market and say you want to buy coffee, there are some pre-packed coffees maybe in 200 grams and 500 grams. So maybe 200 grams cost $2, 500 grams cost $5. But the cost per 100 gram is the same at $1 per 100 gram. So basically heat capacity is like the $2 for 200 grams, $5 for 500 grams. But the specific capacity is just like the cost per 100 gram, $1 per 100 gram. So to put some context into actual physics, the heat capacity of 200 grams of water is definitely lower than that of 500 grams of water, but they all have the same specific heat capacity. So this is the key difference between heat capacity versus specific heat capacity. Heat capacity is the total energy required to produce unit temperature change, whereas specific heat capacity is the energy required to produce unit temperature change per unit mass. And then the SI unit is basically just joules per kg per Kelvin. So now, so water or oil, do you know which one has a higher heat capacity? Okay, if you are thinking that water is the one that has higher heat capacity, then the answer is totally wrong. The answer is actually I do not know. Okay, which one has higher heat capacity really depends on mass as well. Okay, not only based on specific heat capacity. What I do know for sure is water will definitely have a higher specific heat capacity than oil. If given the same mass, therefore, oil should heat up faster than water using the same heat source. But if let's say my oil is 100 gram and 100 kg and the water is only 1 gram, then I'm pretty sure that 1 gram of water will actually heat up faster than the 100 kg given the same heat source. So therefore, in this particular case, then I would have said that water has a lower heat capacity than the 100 kg of oil. But the 1 gram of water have a higher specific heat capacity than the 100 kg of oil. So a material with a smaller heat capacity will actually heat up to a higher temperature, compared to one with a higher heat capacity when the same amount of heat energy is actually absorbed. Okay, let us try to identify the error below now. The specific heat capacity of a substance is defined as the amount of energy needed to raise the temperature of a 1 kg mass by unit temperature. Now, there are actually two mistakes here. The first mistake is the word 1 kg. The second mistake is the fact that it is actually missing some very important keywords, and they are without a change in state. When we are defining a quantity, it's actually wrong for us to express it in terms of the unit of quantity. Like, for example, in this case, it is actually wrong to say that specific heat capacity is applicable to only things like 1 kg of mass. Who is to say that joules per Kelvin per gram is not specific heat capacity? Even if let's say it is not per gram, per milligram, per teragram even, okay, they are all still known as specific heat capacity. Just that in terms of the per unit mass, we are using different kind of per unit mass. So that's why when you are actually defining specific heat capacity, you cannot use the word 1 kg. It should be replaced by unit mass. And this is actually a very common mistake from students when we are asking them to define specific heat capacity. And in the same spirit, don't go and accidentally define it as per Kelvin or per degree Celsius. The correct keyword is actually unit temperature. Now, the second mistake is the fact that the line without going through a change in state is missing. These few keywords is actually also essential for the definition of specific heat capacity. Okay, so now move on to problem solving. The way to solve this kind of question is all very standard. It is essentially always be using conservation of energy. So basically, energy gained by one body is equal to energy lost by other body or the other bodies. So if heat is actually provided by a source and there's also heat lost to the surrounding, for example, boiling water. Boiling water is actually higher temperature than the surrounding, so heat is actually lost from the water to the surrounding. So for questions like this, the conservation of energy equation basically become heat supplied is equal to energy gained by the body plus heat lost to the surrounding. We have another type of question where the object on top of gaining heat from the heat source is also gaining heat from the surrounding. Like for example, in this case, ice. Ice in this case is gaining heat from the immersion heater. It is also gaining heat from the surrounding since ice is actually lower temperature than the surrounding. And then for such cases, the equation just become heat supplied by the heater plus the heat gained from the surrounding will be the total energy gained by the body. Okay, if right now you don't feel like you quite understand everything that we have discussed so far, don't worry too much about it. We are going to start solving some examples. At the same time, for this type of question, the one like ice, okay, you should take a look at what example with visible thinking question 1, which can be found in page 16. Okay, and then by looking through all these word example, you should have a pretty good idea thereafter. So now let's start solving the first word example 1. We here have a copper calorimeter of mass 0.12 kg containing 0.1 kg of paraffin oil at 15 degrees Celsius. So first and foremost, if you actually do not quite know what is a calorimeter, okay, it is basically this diagram here. For calorimeter, the key thing and special thing is that you are supposed to assume that it is insulated and there should be no heat exchange between the paraffin here with the surrounding environment, with the external environment. So we have here the calorimeter having a mass of 0.12 kg, and then inside the calorimeter, we have 0.1 kg of paraffin. And then we are going to put in some hot aluminum into the paraffin, and then finally you are required to actually calculate the specific heat capacity of the paraffin. So in this case, after the hot aluminum is added into the calorimeter, for sure there is going to be some heat exchange between the aluminum and the rest of the item, since the temperature is actually different. So basically, to find the specific heat capacity of the paraffin, then what we need to solve is, of course, heat gained by the copper calorimeter and the paraffin must be equal to the heat loss by the aluminum. Then basically we are just going to use the equation Q equals to mc delta temperature to find the individual heat gain and heat lost. And then the final temperature is actually given to be at 27 degrees Celsius. So from there we can actually find the absolute value of the delta T. For example, the calorimeter and the paraffin was initially at 15 degrees Celsius. So the change in temperature is of course 27 degree minus 15 degrees Celsius. Okay, and at the same time, we know that initially the aluminum is 100 degrees Celsius. So we can find the change in temperature of the aluminum by taking 100 minus 27 degrees Celsius. And then thereafter solving, we can get the specific capacity of the paraffin to be 2440 joules per Kelvin per kg. Okay, at this point in time, you may be wondering, should you be changing this to absolute temperature Kelvin? Well, you can, but basically when you want to change it to absolute temperature, you'll be adding 273.15 to the 15th degree. You'll also be adding the 273.15 Kelvin to the 27th degree. Ultimately, you are taking a difference between them. So therefore, this 273.15 will also be cancelled out. So in this particular case, whether or not you change it to Kelvin, that's fine. But if you choose to change it, then so be it. Okay. It is actually a good habit to remember to change it. So I will not discourage you from changing it. Now for example 2, here you have a metal block mass 2 kg being heated by a 60-watt electrical heating coil until it reaches a constant temperature. For part 1, you're required to calculate the rates of heat loss to the surrounding, and then for part 2, if the heating supply is cut off and the metal is observed to cool initially at 4 degrees per minute, calculate the heat capacity of metal. So take note that you are supposed to calculate the heat capacity, not the specific heat capacity. Okay, for this example, you should attempt to try this out on your own first, but for the sake of time, I'll continue to go through it right now. But should you want to try it out yourself first, then pause the video yourself. Now, I have highlighted some keywords in this question. So first and foremost, constant temperature. What does constant temperature tells you? Constant temperature must be telling you that the rate of heat loss is equals to the rate of heat gain. And why is that the case? Because if you imagine if the rate of heat loss is actually less than that it is gaining, then it must be raising temperature. If the rate of heat loss is actually more than the rate of heat gaining, then it must be losing temperature. So therefore, for part 1, it's actually extremely simple. Once you can actually rationalize the keyword constant temperature, you'll realize that the rate of heat loss is exactly equals to the 60-watt heat source. Okay, and then for part 2, I highlighted the word initially. Why is initially actually important? Because initially, when the heat supply is being cut off, we know that the rate of heat loss must also be 60 watt. Perhaps after some time when it has actually dropped in temperature, then the rate of heat loss is possibly going to be lower. But initially, the rate of heat loss is still going to be 60 watt. So using this, we can start to calculate the heat capacity of the metal. So the other important information here is that the metal is losing at 4 degrees per minute, which essentially give me the delta T over time. So basically here we have Q. Q over T is the rate of heat loss, and Q should be equal to MC delta T. Or in this case, since we are solving for heat capacity, instead of looking at MC delta T, we should be looking at the heat capacity multiplied by delta T. So with this in mind, we have C delta T over T, and then we know that this delta T over T is basically my 4 degrees Celsius per minute, which is 60 seconds. Okay, and then we can start solving for the heat capacity thereafter. So that's it, heat capacity should be 900 joules per Kelvin. Now we move on to the last section on specific heat capacity, where we are focusing on gases. Whatever that we have been solving just now are all about the specific heat capacity of solid and liquid. And there's one key difference between solid and liquid versus gases. And the key difference is that volume change for solid and liquid when temperature is changing is actually negligible. But for gases, the volume change is not negligible when temperature is changing. And that actually has a huge impact on how to calculate the specific heat capacity of gas. Hence, for gases, whenever we are calculating the specific heat capacity, we have to specify, is it under constant volume condition or is it under constant pressure conditions? So obviously, under constant volume condition, there is no change in volume. Whereas under constant pressure condition, the volume will increase when the gas is being heated. The amount of heat energy absorbed by the gas for constant pressure is expected to be larger than constant volume condition because of the increase in volume. We'll be discussing this later because it involved the most important concept for this particular chapter, the first law of thermodynamics. So we will leave the detailed explanation after we have went through the first law of thermodynamics for this particular scenario. Okay, but like I said just now, it is not necessary to distinguish the difference for solid or liquid because the change in volume per unit temperature is often very small and hence can be neglected. Specific capacity is all about the thermal energy, how much thermal energy is required to raise temperature without a change in state. So obviously, there must be another category of heat where it is all about changing state without a change in temperature. And this is what we call latent heat or specific latent heat for that matter. So for a substance, when it boils or when it melts, it doesn't change temperature, okay? Because the heat that is provided in this case, or we call the latent heat, is actually the amount of heat energy absorbed that is helping it to change state without changing any temperature. And for specific latent heat, we basically split them into two types. One, we call it the specific latent heat of vaporization, which is essentially helping a change of state from liquid to gas or vice versa. So to be more specific, specific latent heat of vaporization is defined as the energy per unit mass required to change a substance from liquid phase to gas phase, or in fact is vice versa, without a change in temperature. The other category is what we call the specific latent heat of fusion, which essentially focuses on the solid to liquid or liquid to solid. So therefore, in more specific details, the specific latent heat of fusion is defined as the energy per unit mass required to change the substance from solid phase to liquid phase or vice versa without a change in temperature. Both of these quantity is given by the equation R is equals to Q over M, where L represents the specific latent heat and Q is the amount of heat energy, M is the per unit mass. So therefore, L specific latent heat is equals to heat energy per unit mass that is required to help a substance change state without a change in temperature. In normal cases, when we write the equation, we will also subscript it with V to represent specific latent heat of vaporization, or F to represent specific latent heat of fusion. So let us quickly compare once again between specific heat capacity as well as latent heat. Specific heat capacity, once again, is the energy provided to increase temperature without a change in state. So what type of energy does this heat energy provide? Essentially, the energy provided mainly goes into increasing Ke of the random motion of the molecules of the substance. And from the previous video, you should have already learned that the Ke due to random motion is proportional to temperature. And that is why for specific heat capacity, this energy, when it goes into increasing Ke, will cause temperature to change. And because there is no change in state, there is very little change in volume. And because when the volume doesn't change much, that means that the intermolecular spacing didn't change much as well. So that means the molecule is relatively still equally spaced apart. And this is why intermolecular PE stays relatively constant. Let me help you understand this a little bit. If you imagine GPE, if I have something that is really near Earth, we say that the GPE is actually low. But if I project this thing higher up, okay, into the vertical sky, then we will say that the GPE has increased, it has become higher. So essentially, GPE increases when two objects are further apart. That goes the same for intermolecular PE. Okay, intermolecular PE also increases when the molecules are in fact further apart. And that is why when I say here, when there's no change in state and therefore there's no change in volume, and therefore there's not much change in the intermolecular spacing, I can conclude that intermolecular PE stays relatively constant. Now for specific latent heat is essentially energy provided to change state without a change in temperature. So since there is no change in temperature, the Ke due to random motion remains relatively constant. And the change in state will result in the breaking of intermolecular bonds. Okay, so the nature of the forces will change, and that is why this energy all goes into breaking the bonds and therefore increasing the intermolecular PE. Moving on. After we have already compared the heat capacity and latent heat, now we will compare between the two latent heat themselves. And I state specific latent heat of vaporization is actually larger than the specific latent heat of fusion. And the reason is really as follows. The separation between gas molecule is much bigger compared to both liquid and solid. So when I say that I am vaporizing something, I'm changing it from liquid to gas, the molecules are going to become much more separated. And like I mentioned just now, the larger the separation, the larger the molecular potential energy. And therefore, energy provided in this case to separate the molecules must be far larger, okay, from liquid to gas, must be far larger than a change in state from solid to liquid. And that is why the specific latent heat of vaporization should be much larger than the specific latent heat of fusion. Moreover, the larger increase in volume in vaporization also means that there is also work to be done to push back the atmospheric pressure. So from liquid, before it can escape into as a gas molecule, the gas molecule will need to push back the atmospheric pressure, the gas molecule that is already present in the atmosphere. So in order to vaporize, the gas molecule will need to push it back. So this requires energy. This requires work to be done. And that is why this additional aspect of vaporization will also make specific latent heat of vaporization to be larger than specific latent heat of fusion. With most of the theories done, we'll now look at how we can apply them to graph. So we have here a temperature versus time graph. And for section where there's a horizontal line like here and here, basically what it means that there is no change in temperature and therefore the substance must actually be undergoing a change in state. And given that it is the same heat source, of course the longer the duration, the more heat is provided, because heat is basically Q equals to power times time. And all this heat is actually providing for the change in state, and therefore it must also be equal to mass times the specific latent heat in this case. And from the graph, you can see that there is a significantly longer period of time for water to be fully vaporized. And therefore, it must also mean that there is significantly more thermal energy required to vaporize the water. And the very key reason is like what we have already discussed just now, because we are breaking bonds completely in this case so that the molecules can go really far apart. Therefore, the intermolecular PE will increase much more significantly during vaporization, and that is why it actually requires significantly more thermal energy as well. And for the section where the temperature is actually rising, for example here, we know that these are the section that is probably relevant to specific heat capacity. And like all other graph, one of the most important thing for graph is actually the gradient, of course. And gradient in this case can actually help us find the specific heat capacity. How does it help us find? Basically, power is equal to Q over time. And in this case, since we are talking about the specific heat capacity, Q is essentially equals to MC delta temperature. And just manipulate the equation a little bit, we get delta temperature over time. Delta temperature over time is basically the gradient, because temperature is the y-axis, time is the x-axis. The change in temperature over the duration gives me the gradient. So essentially, I can rewrite the equation into power supply equals to mass times specific heat capacity multiplied by the gradient. Just manipulate algebraically, we can make specific heat capacity as the subject, and therefore we can find the value itself through the gradient. Okay. So with this explains, now think. Do you think that the steeper the gradient actually indicates a higher or lower specific heat capacity? Well, the steeper the gradient in this case actually means lower specific heat capacity. How can you see it? If you recall the equation that we were trying to derive just now, we have the power supply equals to mass multiplied by specific heat capacity multiplied by the gradient. So if we make specific heat capacity as the subject, you realize that the gradient is actually the denominator. And therefore, the sharper the gradient, the lower the specific heat capacity. So mathematically, you can see that happening through the equation. But at the same time, you must also be able to think intuitively along the line that when the gradient increases, what it actually means is that the substance can gain temperature faster. So specific heat capacity must be low so that given the same power source, the same amount of energy can actually cause a higher temperature change in a given time. And that is why the steeper the gradient, the faster the temperature is changing, the lower the specific heat capacity. So now we'll do some work example to help us consolidate the learning. In example 3 here, we have an electric kettle of 2 kilowatts heating element. So basically this is telling me that there is a power source that's providing 2 kilowatts of energy per unit time. It also has a heat capacity of 400 joules per Kelvin. Something for you to take note here, this is the gross heat capacity, it is not the specific heat capacity. So therefore, to find the energy required to raise the temperature per unit Kelvin, okay, we do not need actually the mass of the kettle. We just need to multiply 400 with the amount of temperature change that has occurred, and then we can find the total energy required for it to do so. Here we also have 1 kg of water at 20 degrees Celsius placed inside the kettle. With this mentioned, I will also assume that the kettle also have the same temperature at 20 degrees Celsius. Then the kettle is switched on, and it was found that 13 minutes later, the mass of the water is now 0.5 kg. This tells me that initially there's 1 kg of water, and now there's only 0.5 kg of the water. It must mean that the water is actually boiling. So 13 minutes later, the temperature of the water is actually 100 degrees Celsius. And in fact, half of the volume has already been vaporized. So that means I must be calculating something relating to the latent heat of vaporization. And indeed, in the question itself, I'm really trying to find the specific latent heat of vaporization for the water in the kettle. we are provided with specific heat capacity of the water to be at 4.2 kilojoules per kg per Kelvin, and we are also required to state the assumption. So for most of the cases, most of you will be able to come up with this assumption yourself. I'm going to assume there's no heat loss to the surrounding, but here I added some comments. Since there's only one scenario, we cannot cancel the heat loss away from simultaneous equation. You perhaps may not quite understand what do I mean right now, but please keep this in mind because in the later example, in example 4, I'm going to illustrate what am I trying to say here. Okay, but as of now, it is good enough for you to assume that there's no heat loss to the surrounding. So essentially, all the heat provided by the heater must be going into the heat gained by the water, as well as the heat to vaporize half of them away, as well as the heat gained by the cathode. So the heat gained by the water is basically MC, delta temperature of the water. The heat gained by the cathode must be C, delta temperature. Why do I say C delta temperature again? Because we are given the gross heat capacity in this case. And then the heat to vaporize is essentially MLF. But what is this M? This is the MLV, sorry, not MLF, MLV. But what is this M in this case? This M is not the mass of the water, it is the mass of the water vaporized. So therefore, the M here and the M here will be different. Okay, the first M will be the total mass of the water, which is basically the 1 kg. The second mass is the mass of the water that's been vaporized. So 1 kg minus 0.5, therefore 0.5 kg. I can already start substituting number into the equation. Heat provided by the heater is basically power, the 2 kilowatts multiplied by the 13 minute. And then I have the mass of the water times specific capacity of the water multiplied by the change in temperature, which is basically 100 degrees Celsius minus 20 degrees Celsius. And then we have the heat gain to vaporize, which is basically MLV, and then heat gain by the cathode, C times delta temperature. So substituting number into the equation, we will be able to calculate the specific latent heat of vaporization to be equal to 2.38 times 10 to the power 6 joules per Kelvin per kg. Okay, so now moving on, as I mentioned just now, we are now assuming there's no heat loss to the surrounding. Okay, and if actually heat loss is not negligible, then the experiment must be repeated with a different power input perhaps, but maintaining the same temperature. Why do we need to maintain the same temperature? Because theories actually tells me that the rate of heat loss is by right proportional to the difference in temperature. The difference in temperature between the surrounding and the object itself. So if let's say there's a greater difference in temperature, say the object is let's say 100 degrees Celsius versus a temperature of 20, so there's a difference in temperature of 80 degrees Celsius, the rate of heat loss will be high. But if let's say the object is at only 30 degrees Celsius, and there's only a 10 degrees Celsius difference in temperature with the environment, the rate of heat loss in this case will be significantly lower. Okay, because the theory once again states that rate of heat loss is actually proportional to the difference in temperature. So if let's say I can actually vary the experiment with a different power input and still maintaining the same temperature, the rate of heat loss is actually a constant. But in this case, I can actually come up with two equations to eliminate the rate of heat loss. Okay, and now I need you to actually include the word rate of heat loss into your lecture notes, because in the lecture note, I think what we have written there is basically to eliminate heat loss. By heat loss is the gross amount of energy, that means the unit is joules. What can be eliminated by right is the rate of heat loss, which is actually a power equation, power quantity. Okay, so now I explain this in more detail by looking at work example 4. So in work example 4, we have a liquid that is maintained at its boiling temperature by means of an electrical heater. And then in this case, we are given two power input P1 and P2, and therefore they will result in different rates of loss of mass, M1 and M2. Something for you to take note in this case, capital M1 and capital M2 is not referring to the mass of the liquid per se, but it is referring to the rate of loss of mass of liquid. So essentially, I'm trying to tell you that the unit of M1 and M2 is actually not kg, it is actually something like kg per unit time per second, okay, because it represents the rate of loss of mass of liquid. So obviously, the higher the power, there will be a greater loss of mass of liquid, okay. And also in the question, it states that for each power of the heater P1 or P2, the rate of heat loss to the environment, or basically power loss to the environment, is the same. And why is that the case? Once again, the theory tells me that the rate of heat loss is actually proportional to the difference in temperature. So in this case, if let's say the boiling water or the liquid is actually maintained at the boiling point, whether P1 or P2, the temperature of the liquid is the same. Temperature of the environment should also be the same. Therefore, the temperature difference is the same in both cases of P1 and P2. And that is why the power loss to the environment will be the same as well. So finally, in this question, we are required to derive an expression for the specific latent heat of vaporization of the liquid. So now some of the things that you must rationalize here. We are given two sets of conditions. So even if the question did not tell you that there's a rate of heat loss to the surrounding, unlike in this case, the question did specify, but even if the question did not tell you about the rate of loss of the power to the surrounding, you should never assume it to be zero because you're actually given two sets of conditions. So what this means is you actually can manage to create two simultaneous equations and solve them accordingly. So there is no need to assume the rate of heat loss to the environment is zero. Okay, whenever there's two sets of conditions given, you should never assume the rate of heat loss to the surrounding to be actually zero. So therefore, to solve this question, let H represent the rate of heat loss to the surrounding since it's given as H. So therefore, power input is basically the rate of loss of liquid multiplied by the latent heat plus the rate of loss to the surrounding. So I can actually have two equations, P1 equals to M1L plus H, P2 equals to M2L plus H. And then all I need to do is to take equation 1 minus equation 2. Essentially, I have P1 minus P2 will be equal to ML1 minus M1L minus M2L. And then the H I can cancel off. Factorizing L out and then make L the subject, I will be able to get this expression here. Okay. And in normal questions, let's say you are able to calculate the specific latent heat. In this case, then I will be able to substitute this value back into the equation to actually find the rate of heat loss. Okay, once L is actually known. And also, just in case, do not misunderstand or misinterpret the capital ML. The capital ML is actually not Q. Okay, it is not an energy quantity. In fact, it is actually a power quantity. It is an energy over time quantity. And why is that the case? Because capital M1 is actually the rate of loss of mass of liquid. Meaning to say that if I want to rewrite capital M1, it will be the total mass that has been vaporized over the duration that this thing has taken place. So essentially, if I want to rewrite capital M, 1L, it should have been written as ml over T. This numerator ml refers to the heat provided, the total heat provided in this case. And that is why capital ML should be equal to a Q over T quantity, which is equal to a power kind of quantity. It's an energy over time kind of quantity. And that is why I can actually equate them to the power of the heater plus the rate of heat loss to the surrounding. Okay, so just in case, do not misinterpret M1L as Q. It is definitely not Q. Okay, so now moving on. In this example, we realize that heat is actually the one that is lost to the surrounding, and that is why we write the equation in this way. Power supplied is equal to the rate of energy gained by the power plus the rate of energy lost to the surrounding, and therefore we have the quantity H on the right hand side of the equation. If let's say we are doing experiments using ice where the heat is gained from the surrounding, then the equation should become power supplied by the heater plus the rate of energy gained from the surrounding to be equal to the energy gained by the body. Okay, so in this case, H will therefore be on the left hand side of the equation. Okay, it looks like it's a minute difference, but it can be a significant difference. Okay, so please take note whether is it in this case heat is lost to the surrounding, or in fact in another case possibly using ice, heat will be gained from the surrounding, and therefore write your equation correctly. Okay. Finally, let us discuss something a little bit more, okay, something extra. So let's say we have ice at 0 degrees Celsius versus water at 0 degrees Celsius. And let's say I do a lot of cooking during the circuit breaker period. So I want to cool something hot down, for example, my hot wok. So do you think it is a more efficient process? Okay, ignore the logistic, but do you think it is more efficient physics to put the wok in the basin of ice at 0 degree? Or do you think it is more efficient to actually put the wok in basin of water at 0 degree? Which method is actually better to cool the hot wok down? Or are they actually the same? Okay, in fact, there's a difference, and putting the wok in the basin of ice is actually better. Why is that the case? Because think about it. In order to melt the ice, I first and foremost need to provide some heat from the wok to first melt the ice to water at 0 degrees Celsius. Okay, and after melting the ice already, the wok will have already cooled down by quite a fair bit. Okay, at the same time, now the water is still at 0 degrees Celsius. It can further cool the wok down further. Okay, so therefore, the remaining heat will overcome the heat capacity of the ice and therefore cool down the wok even further. If I were to use the water directly, then water would immediately increase in temperature. And that is why it is actually less effective to cool the hot thing down, okay, in this case, by using water at 0 degree. It is actually much more efficient, or in terms of physics, it is actually much more effective to actually use a basin of ice instead. Okay, all because first and foremost, the heat from the wok will actually need to melt the ice, and thereafter the water can still further reduce the temperature of the wok. Okay, so finally we are done with the first part of the lecture, which is all about the specific heat capacity as well as the specific latent heat. In the next lecture video, we will then focus on the more important stuff for A level, which is to understand internal energy in detail, as well as learn and apply the first law of thermodynamics, which essentially is about what causes internal energy to change. Okay, so see you in the next video.
Did you get any of that?
Sure, Bo,
Understand
your online source of
interesting physics lecture.